This is the IEEE Computer Society Distinguished Visitors Program webinar series. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays all intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Good morning, good afternoon, and good evening to everyone joining us around the world. Welcome to our first in the Distinguished Visitors Program webinar series. Before we go any further, my name is Kerry Cosby, and I'm the Chapters Manager here at the IEEE Computer Society. I oversee our more than 500 professional and student chapters around the world and manage our Distinguished Visitors Program. Topics in this webinar series will range among those listed in the video presented earlier and more. Before we get started, I'd like to get a couple of housekeeping tasks out of the way. You can ask any questions in the Q&A panel. Dr. Zeigler will answer as many questions as he can following his presentation. The webinar is being recorded, and the slides and the recording will be made available within a few days of this webinar. Today's speaker is Dr. Bernard P. Zeigler, Professor Emeritus of Electrical and Computer Engineering at the University of Arizona and Chief Scientist at rtsync.com, and a distinguished visitor chosen from among many global nominees to represent the program. He received a PhD in Computer and Communication Sciences from the University of Michigan, an MS in Electrical Engineering from MIT, and a BS in Engineering Physics from McGill University in Montreal. Dr. Zeigler has held faculty appointments at the University of Michigan, the Weizmann Institute in Israel, Wayne State University, the University of Arizona, and Arizona State. Dr. Zeigler is currently affiliated with the Center of Excellence in Command, Control, Communications, Computing, and Intelligence at George Mason University. Dr. Zeigler, thank you for presenting today. The floor is yours.
Thank you very much. It's a great pleasure to be a speaker on this series, and I look forward to interacting with the audience. I'm hoping to stimulate your interest enough to come back and get the slides and go into more depth into the discussion, because a short time available, I may not be able to finish everything and certainly not get into great depth. But I'll try to give you a good outline of what the issues are and how I think we might be able to proceed. Especially, I'm trying to convey the idea of modeling and simulation as representing a core capability needing to address today's complex, adaptive system of systems engineering challenges. And I'll say a little bit more soon about system of systems. They really characterize the current technology developments here and throughout the world. There's another concept called model-based systems engineering that has been growing in the last several years, and it supports dealing with these system of systems. But it needs to include more of modeling and simulation, the ability to develop what we're calling multifaceted models, as well as analyzing them with computationally powerful and correct simulation engines. Also, software engineering has become the primary implementation for system-of-system development, so it must also be brought into the discussion. So we'll discuss the potential for closer integration between these three streams, which are kind of run by communities that often are not aware of each other and could benefit from closer collaboration. So here's a presentation on modeling and simulation in support of systems and software engineering. As I indicated, model-based system engineering is the approach that has become and will become dominant for dealing with complex systems. And it has model-based system engineering language or language concepts to describe systems from an architectural point of view. And that as well has happened in software engineering for design of software systems. But my point is that both approaches need modeling and simulation to support the exploration of what the architecture does, to test it before fielding the real system, to deal with conflicts. I'll show you an example in a bit that could arise in the operation of systems and for verification and validation. So as examples, smart cities and all the kind of AI-based technologies that are currently being developed, such as driverless cars and so on, can fall into that system of systems engineering domain. And SysML is one of the kinds of languages that have been developed, and lifecycle ML has recently been developed. So these are ways of describing, as I said, architectures or ways systems are built from their components. Similarly, in software engineering and in the intersection, you could say, between software engineering and system of system engineering, such as cyber physical systems and Internet of Things, that the need for architectural design languages has come about. And UML is very well known as Universal Modeling Language and or Unified Modeling Language. And also from the software engineering systems people, system of systems architectural design language is an example. But I'll be talking about DEVS, Discrete Event System Specification, which is modeling and simulation kind of a concept and language. But I'm talking about having it be integrated into the development for the complete system, where you might start with the architectural specification. So these two streams, or three streams, model-based systems engineering and modeling and simulation, need to expand their purview to link up. I'm quoting here from a recent thesis from Naval Postgraduate School, which makes the point that model-based systems engineering should encourage development of architectural products that directly support development of modeling and analysis products, and should support continuous interaction between architecture developers and modeling and simulation developers to clearly link these products to solve the defined problem. And this would enable design solutions to be explicitly linked to the defined problem as a result of this connected, interdependent process. So inversely, modeling and simulation should enhance the architectural products from modeling MBSE with increased realism as necessary to solve the defined problem. So as coming out of architectural level, you have quite a high level of abstraction, and this level has to be brought down further and further to more realism to actually deal with the problem at hand. So there has to be continuous interaction of architectural developers, MS developers, to do this clearly linked with the and this should enable continuity of elaboration. So as you more and more detail, adding more and more detail, you should be able to also trace back from the high resolution simulations that ultimately allow testing of the design back to the initial concepts in the architecture, because more than likely a lot of problems will be discovered in the simulation that need to then be corrected back in earlier stages. So as a kind of motivation example, before getting into some of the theory that supports the kinds of things I'm saying, here's an example from the European project involving a few large companies in Europe and several universities. It uses the DevOps approach of life cycle engineering, and going from initial concept all the way through design, fielding, and including continuous interaction with the product and system as it has been developed and is running. In this particular case I'm talking about, there's a use of devs-based simulation to manage what's called the actuation conflict problem. To give an idea of what that is, at the user end, there may be many people or other components that are trying to change some particular device state somewhere down the line, such as turning on an air conditioner or opening a window or some such thing somewhere remote. This goes from the cloud down through the edge devices and into the actual location and the physical areas where these actuations, turning on, turning off, and so on, occur. And there can be obviously conflicts if these are done by remote people or systems that have no real connection to each other. So somebody might be wanting to close a door while another person might be wanting to open a window. And this might create a conflict for trying to heat the room or something like that. So here there's systems are being worked on to manage this kind of activation problem. And they are using at the simulation level the dev's approach. So I'll just go through that. The actuation management itself is done through rule-based actuation languages, and those are then verified through formal analysis, where they are converted to finite state machines, and model checking approaches based on logic are used. But that really can't cover all possible problems. So simulation is needed, and they're then using the devs-based simulation to test before fielding and also during fielding, to check that all the possible conflicts are resolved, because in the simulation you can include more and more detail about what the actual physical system is like, and what can actually happen when different actuations are put on. So with that kind of motivation, I'd like to go through a history of model-based system engineering, MBSE, and how discrete events system specification devs interacts with it. The way I trace it, it goes back to Professor A. Wayne Wymore at the University of Arizona, and his book in 1967, where he developed the theory of systems engineering. A lot of theories of the same sort about systems as the way to describe both control systems and automata were in vogue and being developed at the time. Model-based systems engineering then he described in a book in 1993, and I think independently, Grady Bruch and his colleagues developed the unified modeling language in 1995, and that became the systems modeling language, or was elaborated to it to include more specifications for such things as requirements, and had some influence from the model-based system engineering Wymore. On the other side, I in 1976 developed theory of modeling and simulation and the devs concept within it, partly based on Wymore's system theory. And so now we're talking about how these two streams can come together. So on the hand side, we have the modeling capabilities of devs and the simulation capabilities to describe complex systems. And on the left-hand side, further developments of the SysML and other similar approaches. And the question is, can these streams now come together so that an end-to-end kind of solution, as I indicated before, can come about? So tell you a little bit more about how that devs and the system to each other. This is in a recent edition of my original book, and the idea of iterative specification is further elaborated in that book. This is a basic way to specify a system of the sort of Wymore's, But Weimar wasn't concerned with the computation capabilities of systems or how to describe them together. Let's see. Let me see. I'm being told maybe that we can't see the slides. Okay, I think I was forgetting to actually push the push to audience button. So here's a view of the types of systems that can be specified. I was saying that the iterative specification is a basic way to specify a system in an algorithmic form. Weimar was not concerned with the computability of systems, how they could be expressed and computed. So the discrete event concept that I developed was as the primary way to make systems computable with the usual, computer systems we have. And this then led to being able to describe different types of systems, and especially hybrid systems that include both event and continuous components. So devs itself way to specify a system, and a particular kind of system, a system where time is goes through in a continuous manner, but events are what drive the state changes, and events occur over time rather than the system being stepped in time steps, fixed time steps to updated states. Events occur and are scheduled to occur, and they change the states of the system and produce inputs and outputs. Now, the devs also, as we indicate now, is capable of simulating any system described at least through the to describe and simulate and allow hybrid systems, systems that are now being associated with cyber-physical systems, both including computation and physics components, physical components. So going on to the next slide, which I'm hoping you see, framework for modeling and simulation. There are two kinds of ideas involved. One is levels of system specification, which allows us to describe systems at different levels. And one is the lower level is treating the system as a black box, and we know its input and output behavior. And levels then increase in more and more known, more and more structure, we'll say, placed and known about inside the box. Ultimately, we can describe the system as built up of components that interact, that are coupled together, and that is where simulation often starts. So on the other side, this system is used to describe the elements of a framework for modeling and simulation, where the framework entails the real system being modeled, the model that is being used, or there may be several models, different levels of resolution, and the simulator that's used to simulate or execute the model. The model is a system in Weimar's sense, and or needs a set of instructions to make. And so the dev's concept of events is the most likely or most efficient way of those instructions. And the simulator is then that is matched up with the dev's modeling formulas. So those constitute the basic elements, but also there's a concept of experimental frame where it represents what the interest is in doing the simulation, what questions are being asked and what conditions are being put onto the system. Under what conditions are we studying the system? So that with each level, there's also a concept of morphism or equivalence. And I can't go into great detail, but these allow us to describe or check or talk about when systems described at those levels are equivalent, when they actually have the same behavior or same structure, and allow us to infer from higher levels to lower levels what that equivalence holds or not. So when we think of it, we're modeling, we go up the levels. We're trying to get more and more knowledge about what the system does. Whereas in simulation, we start from the high level, make assumptions and hypotheses, and then the simulation is what actually going down from one level down to the lower level. So why should the dev's formalism be the one that is what we're proposing for this unification with MBSE? Well, it has a bunch of properties that can be proved in the same way that Weimar developed the system theory. And these are very important in actually doing the simulation, proving correctness and constructing simulation, and in using it for cyber-physical and hybrid kinds of problems. And in application to system of systems, these concepts of the framework help to actually define in a well-defined manner what the entities we're dealing with and how we should be dealing with them. And also it enables more efficient execution of the simulations so that rather than stepping a large number of components, as could happen in a complex system, every time step and a very small time steps needed, we can reformulate systems to work based on events, and events occur much more rare in rare fashion, so that there's advantages to the efficiency and being able to run much faster, and as well that the devs software allows us to run on different platforms. So from multiple kinds of computers, clusters, and network systems, distributed systems, and on a single workstation or your laptop computer. So I was saying about multi-formalism, and there's a lot of multi-concepts. Mainly, we're talking about having models at different levels of resolution, and they can be simplified using the morphisms, simplified and related to each other, but also composed together and create hierarchical compositions. And that leads to a concept called the system entity structure. So there's Dev's discrete event formalism, but also the system entity structure. So I wanted to just give an example of that with the healthcare system simulation framework that we developed recently in a book with colleagues, where you can see a hierarchical kind of structure. It's a sort of ontology where the different elements are related, but in a hierarchical way that corresponds to building simulations, say from the top down, breaking them into components, and then components further into components. So there's a decomposition concept, which is the aspect. There's the specialization concept, which is the ability to have different component types for a component. And there's a multi-aspect concept, which allows you to have multiple instances of the same kind of component. And that's all kind of interlinked in this structure. And it works at different levels. So we start with the system level, where there's major specializations, like different types of care, and the facet level, where we have the system components, thinking of a healthcare system as consumption and production, and production might be production of diseases, and consumption is disease spread through the population, and the coordination, which is related to how you can try to keep the spread contained, as we know today, is a major problem. Then the scale level, it has to do with the spatial and temporal scales of the models. And then the lowest level is the actual models that we can reuse and make available from well-established sources, or also have new models that need to be developed, partly by composition of the existing ones. This actually represents a pruned version, in the sense the yellow lines are, or the yellow boxes are choices from the tree that's made, so that the eventual selection represents a single simulation model. As an example, talking about work now we're doing, where we're trying to develop a intervention prediction model. I'll go through this where the model is of the environment and the how the interventions that one may be taking at the system level to try and prevent the spread, say, of a disease may be happening. And then there's the real system, which is modeling, and the actual people involved and so on. And the effects of the intervention are observed and evaluated. And all the interactions involved in the system are stored and eventually become available as data to a learning system that is trying to estimate what the parameter values are for the model to enable it to support better and better predictions, better decisions made by the decision maker. So this model is actually described using that system entity structure concept and Dev's modeling components, as I indicated, and then is being worked on to be operating on an infrastructure for health information technology, which I'm sort of illustrating quickly here. This is in Maryland, where there's a CRISP, C-R-I-S-P, information exchange network that will allow or allows communication among hospitals and physicians, and allows tracking of patients as they move around and are treated in different hospitals and different providers. And this information is fed up to a platform called the Central Public Health Central Referral System. And on top of that platform, the prediction model is being developed to run to acquire the data that's being generated, and also to track the patients as they proceed through stages of treatment, and to test out, as we indicated with that learning model, different interventions and learn what the best interventions are over time. This is a little more detail where the model, in fact, is a model of overall stages of treatment. For example, in the COVID case, and the second layer there, the Taiwan example, is a series of stages from undiagnosed all the way to treated and followed up that could be happening, but need to be tracked to make sure that they are happening, and one stage leads to another with high reliability. So now I want to talk a little bit about how devs can support the model-based system engineering. And we have developed with RT-Sync and other collaborators ability to describe models in UML, in particular activity diagram form right now, where a user can draw a diagram, and then this will be automatically transformed into a dev's model that eventually can be run in a simulation manner and provide information about how that activity diagram actually would work, or the system that it describes would work in a more realistic fashion than it could be otherwise. In between the levels or the steps, there's a parameter specification step where the user has to add more and more detail to the model as it proceeds to get refined, as we indicated before. But this kind of level is supported by this operation. So the designer draws the UML activity diagram. The diagram then generates a dev's model, and it can be enhanced to be in the form of a stochastic Markov model with timings and probabilities, and those kind of parameters can be set by the designer and then a simulation run. So here's an idea of the activity diagram and the code generation. The diagram digitizes, you could say, the documentation with well-defined semantics that otherwise would not be well-defined, or as well-defined as they can be now with this concept we've developed. And it improves the expressive ability of these primitives, the decisions, the forks and the joins that are the basis for activity diagrams, and then offloads or pushes down the details down further to the dev's model. So at this point, I may be able to run a video. You can see a typical activity diagram and drawing of this diagram in a user graphical interface with palette. And then the dev's model in the simulation viewer that we have provided in the MS4Me modeling environment. And you can see the green being the messages flowing among the components. And the eventual result is more simulatable and stochastic kind of model that can actually give performance kind of characteristics. So now I have to switch back. As a final kind of example, let me continue on here. I'd like to talk about how this modeling and simulation concept supports test and evaluation as well. Here's a project we were involved in, which had to do with developing a new or extended message protocol language for exchanging of messages between systems, such as between a fighter aircraft and a drone, as shown. The messages can be queries or commands or responses or other information, and they appear in a certain format and are then exchanged among entities. You can think of what's going on as extending an existing document that describes in thousands of pages the protocol. But in order to test it, it has to be converted into a testable form, and that form is, in our approach, is actually a dev's model. In the sense that it can accept input messages and generate output messages that represent, in each case, the entities that are involved. And they go through their states as they receive these messages and transition to other states and generate outputs. So that when you look at a specification for such a protocol, it really boils down to a model of the form of a devs, in our view, that we can then use for testing. So in this slide, we go through a process of converting from a UML specification for a message or message set into a devs model. So that's going from number 1 to number 2. The slide seemed to be a little disoriented where that arc should be on the top. We go from the devs model in number 2 to the inverse devs model in number 3, which is a concept that allows you to take a model and invert it in a way that allows you to test it. I'll talk about that in just a moment. And then that model, the inverse model, becomes a part of a test driver that interacts with the original system to test it. So here's the inverse devs model concept, and it's particularly appropriate in devs, where the model itself has a state. The inverse model has the same state but relabeled. Where the inverse model has an output message, the devs model has an input message, and where the inverse model has an input message, the devs model has an output message. So when the system is waiting for some input, the test model must provide that input, and when the system is generating an output, the test model must accept that input. The interesting thing is that the timing involved with these states is also nicely related in the devs case. So we go from infinite waiting, meaning waiting for something, to finite value, meaning you have to provide an input when the other system is waiting, and so on. And this is then developed into an operational test environment, and we have performed this kind of test where the system developed in UML is converted into its C++ form and communicates with the dev's test model over socket communication using the dev simulation protocol. So here to finish up is an idea of how we might work toward convergence of the two different streams, so three different streams as you like. The International Council of System Engineering has a roadmap that they've developed in which they're talking about how the MBSE concepts can be further extended over time in the next few years to be more and more powerful and actually to intersect and make contact with the simulation capabilities. On the other side, the modeling and simulation can further develop to extend its standards and its framework for integration and coordination needed for system of systems, and extend the capability to convert or allow high-level diagrams to be related more directly to simulation, and the expressive capability of such simulations, and use of that system entity structure concept to support hierarchical models, reusability, and composability. And just to finish off, here's some books that are available, and a link to a talk on this, or a paper on this talk. And this the presentation will be available generally from the IEEE. And my email will also be available, so I'll be happy to interact and answer any questions with people in the audience.
Dr. Zeigler, if you'd like to go through the questions in the question box, the Q&A box, there are some that you might want to answer. You can just look through there. If you'd like. Pardon?
Yeah, a lot of them are about the slides.
Yeah. The ones that are not, you can go ahead and go through those. They'll be marked unanswered.
Yeah, the question is, are there special elements for security, or is it being ignored? So I assume that's about the modeling and simulation developments and so on. All of the issues of security have, of course, have to be taken account of. In this kind of talk, it's hard to include both that kind of discussion as well, but it's something that would be pervasive throughout the development. But also in the case of the medical or the healthcare, the equivalence there of HIPAA, the requirements for patient information, privacy, and so on, those are definitely embedded within the kind of tracking that we're talking about there. Here's a question: how is that simulation enabled with devs different from what Cameo simulation toolkit offers, for example? I'm not familiar exactly with Cameo. There are many simulation software packages around. The difference I've tried to point out is devs is derived and in fact means that it's a way of specifying a mathematical system concept. And that concept provides a firm foundation for describing systems of all kinds, as well as simplifying systems and constructing complex systems, and so on. So it's not just the simulation capability that we're talking about, it's the ability to integrate with other concepts such as model-based systems engineering and to perform discrete event simulation, which I'm not sure, I don't know about Cameo, but may not. Commonly, the simulation softwares are time-stepped and not event-based. Let me see, this question says, as you have observed, these two are closely related. It seems that both have the issue of properly being tied to reality, as well as being properly related to one another. Is that correct? Of course, that is exactly the issue. And the claim I've been making here is that to properly connect the model-based system engineering's abstractions to reality, you need eventually to get to a form that is realistic and can be connected through experiment, through measurement, and so on with reality. And that form is the modeling simulation form. So definitely I think that that's the point that we're getting at. Here's another question. Excuse me. Where can AI play a role in both constructing and validating these models? What is the likely time frame to start seeing AI tools validate models? AI has for long now played a role in constructing and validating models, but that is a hard role to play. The current concentration of AI on deep learning models kind of has moved away from interest in constructing and validating these kind of simulation models. But work by such people as Pearl in inferring from data what underlying causal relations there are can be integrated with the model construction for simulation, and would provide a much more powerful combination than each one has separately. So that's an example where such approaches could lead and could happen in the next few years if we're focused on them. also, on the other side, the complex systems such as the driverless cars and such Internet of Things, as I gave the example, that depend heavily on AI, might now or have now to be tested before fielding and while fielding through simulation means, as I sort of gave an example before. And that's another way that these two areas can interact, because AI, these kind of AI systems will need a lot and very much to go through all the possibilities that they might encounter, and simulation is a way, especially using the system of system and the system entity structure concept to generate all those kinds of possibilities.
Dr. Zeigler, we're at the end of our time. If you want to take one or two more questions before we close out.
Okay, let's see here. There's one. What is the relation between machine learning with simulation and modeling? Okay. Well, it's a relation as sort of I've been indicating with the previous question. The machine learning can support development of models. And for example, the learning system that in the healthcare world that I'm showing can use concept from machine learning to support the learning of parameters. Often you need to consider all kinds of combinations, not just individual sort of settings, but how parameters interact. And this leads to combinatorial spaces that have to be searched. And machine learning concepts can help. We ourselves have used evolutionary programming and such concepts, genetic algorithms, but also reinforcement learning could be used to support the interaction between the environment and the system in a more fundamental way. Okay, I think that's probably all that there is.
Yeah, Dr. Zeigler, I'd like to thank you very much for your presentation today. I'm really sorry that we couldn't get around to everybody's question. I do thank all of you for attending today and taking part very actively. If we haven't been able to answer your question during this presentation, your email's being logged along with your question, so we'll reach out to you via email to answer the questions that we weren't able to answer here in the webinar. As well, I want to let all of you know that we'll be putting on other Distinguished Visitors Program webinars, but we're also going to be doing early career webinar series webinars focusing on business soft skills such as communication and presentation skills, career transition, interviewing tips, among other topics. The first webinar will be on April 23rd at 11 a.m. Eastern Time on personal brand management. This will be presented by Elsa Velasco-Paul, and she's the founder of the M&E Group. The next Distinguished Visitors Program webinar is going to be on April 16th at 7 p.m. That will be presented by Dr. Yanir Baryam, who's the head of the New England Complex Systems Institute, and he'll be presenting an update on the COVID-19 pandemic, the status and prognosis. This event will be brought to you jointly with the IEEE Computer Society Boston chapter. Then on the 7th of May at 11 a.m. Eastern Time, we will have Dr. Bruce McMillan, who's professor at Missouri University of Science and Technology. He'll be presenting on cyber physical security through information flow. Again, I'd like to thank all of you for coming. Registration for these upcoming events is now open. We'll be sending you a link to these future events along with the slides and the recording of this webinar. Again, Dr. Zeigler, thank you very much for your presentation. It was great. And thank you to everybody else for joining us on this webinar today. Have a great day.
Yeah, thank you, and it's been a pleasure.